So, what if I told you the single most important factor determining whether your new EV gets 300 miles of range or, leaves you stranded on the side of the highway has absolutely nothing to do with battery chemistry?
Right. Which sounds crazy, but it's true. It actually comes down to this microscopic, totally invisible twist.
Yeah, a tiny mechanical twist. And that is exactly our mission for today's deep dive. We are looking underneath the hood of the EV industry to explore a highly specific, often completely invisible metric.
And it is single-handedly making modern electric vehicles efficient and reliable. I mean, it's the hidden bottleneck of the entire electric vehicle revolution.
It really is. Because, we constantly hear about aerodynamic designs, autonomous features, gigafactories, all of that. But the actual physical limits of electric mobility are dictated by how accurately engineers can measure that invisible twisting force, right?
Exactly. I mean, the global EV market right now is valued in the hundreds of billions of dollars. You have massive legacy automakers, brand new startups. Everyone's just pouring fortunes into electrification.
Right.
But every promised increase in range, every single claim of better performance, it all has to survive this incredibly grueling testing and validation process first.
And that entire process relies completely on high accuracy data, doesn't it?
Oh, absolutely. It's a ruthless environment in those testing labs. But before we get into the technology itself, we really need to understand why the testing environment has changed so drastically.
Right, because testing a car seems like testing a car, from the outside anyway.
Yeah.
Put it on a rig, spin the wheels, and measure the output.
Well, yeah, but the powertrain paradigm shift between combustion and electric is staggering when you actually get down onto the lab floor.
Okay, let's unpack this. Because I want to know what is fundamentally different about testing an EV powertrain compared to, say, testing a traditional gas-powered internal combustion engine.
Okay, so think about the mechanics of it. Testing a traditional gas engine is kind of like tuning a massive, loud, heavy mechanical clock.
Oh, because you have thousands of moving parts.
Right, thousands of parts. You have literal explosions happening inside metal cylinders. You have heavy gears grinding together. It's very visceral.
Lots of heat, lots of noise.
Exactly. And frankly, it's a bit forgiving of micro inefficiencies because the system itself is so inherently brute force. But testing an electric vehicle powertrain,
Right.
that is like calibrating a highly sensitive, totally silent supercomputer. It is a completely different beast.
Oh, wait, I'm stuck on something right there. Because if an EV motor is entirely electric, like literally a computer on wheels, why do we need a mechanical sensor at all?
That is the exact trap a lot of people fall into, actually.
Oh, really? Because I'm just thinking, why can't engineers just, measure the electrical voltage going into the motor, do some quick math, and call it a day?
Well, you can absolutely measure the electrical energy going into the motor with perfect accuracy. We have great tools for that. But electrical input does not equal mechanical output.
Oh, right, because of energy loss. Like nothing is 100% efficient.
Exactly. When you push electricity into an electric motor, a certain percentage of that energy is just lost before it ever turns the wheels.
Where does it go? Just heat.
Heat is a big one, yeah.
Yeah.
It's lost to thermal dynamics, like heat in the copper windings, but it's also lost to magnetic hysteresis.
Right.
It's lost to the tiny amounts of friction in the bearings. So if you only measure the electricity going in, you are entirely blind to what the motor is actually delivering to the axle.
Wow. Okay, so engineers have to constantly evaluate all these specific parameters, right?
Right, and under rapidly changing conditions too. They need to know drivetrain response to sudden spikes in power, the efficiency of the energy transfer, and crucially, the precise mechanical torque output at any given millisecond.
So if there's a gap between the energy going in and the physical force coming out, that gap basically represents your wasted range.
That's the critical delta. And here's why this level of precision matters so much more in an EV compared to an old gas guzzler.
Because the margins are tighter.
Way tighter. I mean, in a gas car, if you lose a tiny bit of efficiency in the drivetrain, maybe you lose half a mile to the gallon. The driver barely even notices it.
You just fill up the tank a day earlier.
Exactly. But in an EV, if the motor isn't perfectly efficient, you aren't just losing a fraction of a mile, you are actively bleeding battery life.
Oh, man.
And worse, that wasted energy turns into excess heat, which actually degrades the vehicle's core components over time.
So there's literally no room to hide the physical waste in an EV. It just ruins the system.
None. The margin for error is effectively zero. If your torque measurement is off by a tiny fraction, your math tells you the car can go further than it actually can.
Or that the motor's operating cooler than it actually is, which is super dangerous.
Right. Without extreme precision in measuring that mechanical twisting force, the vehicle's overall reliability just plummets.
Okay, so if standard combustion testing tools are too clunky for this, silent supercomputer, what actually replaced them?
Well, you can't just slap a traditional heavy mechanical sensor onto a motor spinning at 20,000 RPMs.
Right, that would just create massive drag and ruin the test completely.
Yeah, the old tools simply couldn't handle the rotational speeds or provide the necessary fidelity. So the industry desperately needed a specialized, hyper-accurate solution to measure this invisible force without interfering with it.
And that led to a major turning point, right, back in 2018.
Yes. A company called Interface, which focuses on advanced force measurement, they introduced something called the AxialTQ wireless rotary torque transducer.
Okay, wireless rotary torque transducer is quite a mouthful.
It is, yeah.
Let's break down the actual physics of this.
Yes.
Because it was engineered specifically for hybrid and EV powertrains, right?
Yeah.
So what is this device? And more importantly, how is it physically capturing an invisible twist?
So at its core, it consists of a high-precision rotor that attaches directly to the spinning shaft of the motor.
Okay, so it spins with the motor.
Exactly. And it's paired with these advanced sensing elements. The way it works is brilliant, honestly. When the motor turns the shaft twists.
But not visibly, right? Like, we're not talking about bending a piece of rubber here.
No. We are talking about a microscopic, practically invisible torsion in solid metal.
A twist so small the human eye could literally never perceive it.
Exactly, but it happens. Now, bonded to that rotor are the sensing elements, which are usually highly calibrated strain gauges.
Oh, okay, strain gauges.
So when the rotor twists, even microscopically, those strain gauges physically stretch.
Oh, I see. And when they stretch, what happens?
Their electrical resistance changes. The transducer takes that minuscule change in electrical resistance and instantly translates it into a precise data point.
Wow. So it is literally turning physical distortion into digital math.
That's exactly what it's doing.
That is wild. It's translating the microscopic stretching of solid metal into a language the engineers can actually read.
Yeah, it's incredible engineering.
But here's where it gets really interesting to me, because it's not just about getting an accurate number. There's one specific capability of the AxialTQ that completely threw me when I was reading the source, and I want to push back on it a little bit.
Sure. What is it?
This system supports simultaneous analog and digital outputs, meaning it spits out the data in two different formats at the exact same time.
Yes, simultaneous outputs.
But, I mean, in an age where my refrigerator has Wi-Fi and literally everything is digitized, why does having an analog output simultaneously actually matter in a real-world testing lab?
That's a really good question.
Why isn't a highly accurate digital readout enough?
Well, it gets to the reality of how dangerous and fast-paced these testing environments are. Think about what is happening in a dynamometer test cell.
Okay, so loud, dangerous, lots of spinning metal.
Yeah, you have an experimental high-voltage motor spinning at incredibly high RPMs under immense, violently changing loads. Things can go catastrophically wrong in a fraction of a second. So you need two distinct things to happen at once. You need to control the test safely, and you need to record the data.
And digital can't do both of those things.
The problem is that digital inherently requires processing.
Oh, because it has to package the data.
Exactly. The sensor captures the data, converts it to a digital packet, sends it to a computer, the computer unpacks it, processes it, and then decides what to do.
But that all takes time.
It takes milliseconds, yeah.
Which is an absolute eternity when a motor's spinning at 20,000 RPMs.
Exactly. If there is a sudden, violent spike in torque, maybe a mechanical failure is starting, a 10-millisecond lag in digital processing means the motor might literally tear itself apart before the safety systems even know there's a problem.
Wow. Okay, so that's why the analog output is critical. Because analog is continuous, right?
Yes, analog is continuous. It doesn't buffer. It has virtually zero latency.
Oh, I see.
It is used for live, real-time control of the testing equipment itself. It tells the machines applying the load exactly what to do right now in that exact millisecond.
So the analog output is kind of like the central nervous system's reflexes.
Oh, that's a good way to put it.
Like if you touch a hot stove, your spine pulls your hand back instantly before your brain even processes the pain. So the analog keeps the test stable and prevents catastrophic failure.
That is a perfect analogy. But reflexes don't have a long-term memory.
Right, you still need to know why you burned your hand.
Exactly. You still need to analyze what happened, and that is where the digital output comes in.
Okay.
While the analog signal is keeping the rig stable and controlling the load, the digital output is being fed directly into massive data acquisition systems.
For continuous high-resolution collection, which you can store, slice, and, run through complex algorithms later.
Right. By having both simultaneously, engineers don't have to choose between safe, real-time control and deep historical data collection.
They get the instant reflexes and the permanent memory without compromising on either. That makes a lot of sense.
Yeah, and having both is what allows for rapid design iteration.
Which is crucial, because in EV development, you aren't just designing a motor once, putting it in a car, and calling it a day.
Not even close. You design it, test it, tweak the software that controls the inverter, test it again. Change a copper winding, test it again.
And if you had to run entirely separate tests for control stability and data acquisition, or if you had constant lag in your systems, that iteration cycle would slow to an absolute crawl.
It would add literally years to a vehicle's development timeline.
That's crazy.
And it's also about the physical adaptability of the testing equipment itself. The engineers at Interface designed the AxialTQ with highly flexible stator and output module mounting options.
Meaning you can physically fit it into almost any complex, weird testing rig an engineer dreams up?
Yes, because an EV development cycle doesn't just happen in a single room. Early on, you might be doing a simple motor bench test.
Like just the bare motor bolted to a table.
Exactly, just the bare motor. But then a few months later, you move to a full drivetrain simulation in a climate-controlled chamber,
where the motor is connected to axles and simulated wheels, mimicking the entire car in freezing temperatures.
Right. And the mechanical flexibility of the stator and rotor design allows the same highly sensitive equipment to seamlessly move across these wildly different testing environments.
Okay, so we have this hyper-accurate, flexible, simultaneous output supersensor measuring the physical twist of the motor. It makes perfect sense that you need this for the wheels, the gears, and the axles.
Right.
But the most surprising insight from this whole deep dive, the thing that really made me stop and reevaluate how I look at EVs, is how heavily battery development relies on these exact same mechanical torque measurements.
It's totally counterintuitive, isn't it? When we think of batteries, we think of chemistry.
Yeah, voltage, thermal dynamics, charging cables. We definitely don't think of mechanical twisting forces.
Right. But think of it as an exchange rate. Let's say the battery is your bank account dispensing cash.
Okay, that's the electrical energy.
And the motor is a storefront turning that cash into physical goods, which is the actual movement of the car.
Got it.
The torque transducer is the auditor standing between them, making sure you aren't being shortchanged.
Because you can't possibly know if your bank account is draining at the correct rate unless you know exactly how many goods the storefront actually produced. That is such a great way to think about it.
Yeah, and that auditing process is becoming incredibly intense right now.
Why is that?
Well, the automotive industry is currently pushing for higher capacity lithium-ion systems. Manufacturers are under relentless pressure to reduce the physical weight of the battery packs, drastically improve their lifespan, and of course, maximize the overall range of the vehicle.
Right. Everyone wants a lighter car that goes further.
Exactly. And because of these extreme demands, battery testing programs have evolved from simple chemical analysis into full-scale dynamic integration testing.
Because they can't just test the battery in a vacuum. I mean, a battery might perform perfectly well outputting a steady voltage on a quiet workbench, but what happens when it's suddenly asked to dump massive amounts of energy to push a 3-ton SUV up a steep hill in 10-degree weather?
Exactly. That's called battery-in-the-loop testing, and it's exactly where the torque transducers come back into the picture.
Okay, so how does that work in practice?
Well, as you said with the exchange rate analogy, the electric motors absolutely must operate in perfect harmony with the battery system. Engineers use the torque transducers to measure the precise rotational mechanical output of the motors relative to the exact amount of electrical energy supplied by the battery in that exact same microsecond.
Energy in, mechanical force out.
Right. This relative measurement is the only way to validate whether a battery and motor combination is actually performing efficiently together.
Give me an example of how that plays out.
Sure. Let's say you are testing a new lightweight battery pack. You run a simulated drive cycle, and you notice the battery is draining 5% faster than your models predicted.
Okay, so something is wrong.
Right, but without highly accurate torque data, you are completely blind as to why.
Oh, is the battery's internal chemistry flawed? Are the cells degrading under load? Or is the battery totally fine And the motor is just failing to convert that electricity into mechanical force efficiently.
Exactly. The torque transducer isolates the mechanical side of the equation. It tells the battery engineers, hey, the motor delivered exactly the force we asked for, so if you're losing energy, the problem is inside your chemical box.
Wow, it's the ultimate lie detector for the powertrain.
Precisely. It really is. As battery manufacturers experiment with lighter designs, higher energy densities, and, new materials like solid-state chemistry, these components have to undergo rigorous validation.
Right, they have to prove they meet performance expectations and strict safety requirements.
And heavy regulatory standards, yeah. If your experimental battery is supposed to deliver a specific power output to the motor, the torque data verifies if that power actually translated into physical movement on the asphalt, or if it was just, lost as heat.
And that verification is what actually accelerates the pace of innovation.
Oh, huge time saver.
Because by capturing this incredibly precise data during every single stage of design, engineers can identify inefficiencies and mechanical issues very early.
Yes. They spot the limitations long before the vehicle design is locked in and sent off to a mass production factory.
Which dramatically reduces the development risk.
It does. And if we connect this to the bigger picture, the transition away from internal combustion to electric mobility is arguably the most significant industrial shift of our generation.
It really is.
But it is a shift built entirely on microscopic margins of efficiency. As the global push for electrification accelerates, technologies like the AxialTQ, these hyper-accurate adaptable measurement systems, they're the silent catalysts.
They are the invisible tools making the physical transition to electric mobility actually possible on a mass scale.
Exactly. Without them, we're just guessing.
So what does this all actually mean for you, the person listening right now, maybe even sitting in traffic? Think about the EV sitting in your driveway, or maybe the one you're thinking about buying next year.
Yeah.
You don't have to worry about the thermal efficiency of its copper windings, or whether the inverter is perfectly mapped to the battery chemistry, because a lab somewhere ran thousands of hours of high-stress iterations on it.
Right. This invisible world of precision torque data translates directly to peace of mind.
Exactly. By catching tiny inefficiencies early, automakers have fewer design revisions, which means they can get better, more reliable, and fundamentally safer electric vehicles out of the factory and onto the road faster.
The measurement technology is basically doing all the heavy lifting in the lab, so the driver never has to give it a second thought on the highway.
It really reframes how you look at these vehicles, doesn't it?
It definitely changes my perspective.
Which leaves us with one final thought, something for you to mull over the next time you see a new electric vehicle roll past you silently on the street. Battery manufacturers are in a constant, relentless pursuit of lighter designs and higher energy density. And every single step forward is validated by these incredibly strict mechanical torque measurements. As these measurement systems become even more hyper-accurate, allowing engineers to chase the ultimate dream of absolute zero wasted energy, will that relentless pursuit of perfect mechanical efficiency fundamentally change the physical shapes, the aerodynamics, and the very materials of the cars we drive tomorrow?
That's a wild thing to think about.
If testing an EV is like calibrating a supercomputer, maybe it's only a matter of time before the cars themselves start to look less like the heavy mechanical clocks of the past and a whole lot more like the silent, hyper-optimized machines hidden within their own testing labs.